Okay, so I'm going to do a little bit of yapping about universal gravitation. So, universal gravitation and Newton's law thereof. So, Newton's law of universal gravitation. Newton set out to find the force gravity exerts between any two bodies. And he said that force, first of all, he said is proportional to the masses of both bodies. So you have to multiply both bodies together. So if m gets bigger, then the force gets bigger. If m2 gets bigger, the force also gets bigger. And he said it is inversely proportional to the square of the distance between their centers of mass. And we know that's really only completely true for a sphere. It's generally good enough, but no matter what the object is. But technically speaking, this is only strictly true for a sphere. But we're going to use it for almost everything, so don't worry about it. And so then there's this constant g. And g is a universal constant. It is equal to, in metric units, or SI, it's 6.67 times 10 to the minus 11. And then, I could tell you the units, but really what you do is you just take whatever units it has to be to make everything work. So force has to come out in newtons, right? So G has to have a newtons in it. And then it's going to get multiplied by a mass and then another mass. So on the bottom, we're going to have kilograms squared, so that when we plug all this in, it cancels out the kilograms squared up there. And then on the top, we're going to have the meters squared to cancel that out. So this is our gravitational constant G. It's a fundamental constant of the universe. Doesn't change from place to place. Actually surprisingly difficult to measure precisely. You'd think we have a really good handle on universal constants these days, and we can know them down to like 8 digits. But actually, we only know this to within like a few tenths of a percent. Which on the one hand sounds like, oh, that's pretty precise, but a few tenths of a percent is actually pretty inaccurate as far as compared to how well we know other constants. But anyway, more on that later. So. So this is sort of excuse me, I just had a little burp there. So this is this is obviously related to little g, and if we want to take the Earth here, for example, and here is the radius of the Earth, r sub e. The Earth has a mass, m sub e, and then we say there's some object here with a mass little m outside the Earth, and we want to find the gravitational force the Earth exerts on this little m thing. So what we do is we take our handy-dandy gravitational equation here, universal gravity equation, and we say the force is equal to this capital G times the mass of the Earth, which I'm calling capital M sub e, and then the mass of our little object, which is little m, divided by the radius of the Earth squared. Okay, so what are these numbers? Well, this is G is of course 6.67 times 10 to the minus 11. Mass of the Earth, I happen to know, is, when you become a physics teacher, you'll know all this crap off the top of your head, times 5.94 times 10 to the 24th kilograms. Little m, I'm just going to say for any old little m, so I'm going to leave little m symbolic. And then our radius of the Earth is 6,384 kilometers, which is of course 6.384 times 10 to the, it's times 10 to the third kilometers, so it's times 10 to the 6th meters. So this is, sorry, this is 24 there. So you can see, just looking at the numbers of these things before I plug them in, we're going to have ME on top is going to be, it's going to have a 10 to the 24th in it. And on the bottom, we're going to have a 10 to the 6th and a 10 to the 6th. So we have like a 10 to the 24th up here, but then we take out a 10 to the 12th down here, so it's actually only going to be like a 10 to the 12th, and then we multiply it by this g, which has a 10 to the minus 11. So really, basically, it wipes out almost all of our powers of 10, and it's going to come out to be a very reasonable number. Let's, without further ado, actually, you know what? Let's just say, I'm just going to go ahead and say we're trying to find the acceleration of this object. So instead of solving for f, I'm going to solve for ma, and then we can just cancel, cancel our m's there. And so then our acceleration from gravity, from the Earth's gravity at this point, near the Earth's surface, is going to be a equals, sorry, not f over m, there we go, capital G times the mass of the Earth divided by the square of the Earth's radius. And let me pull out my little power calculator thing. Yoink. Okay, so let's see. G is, let me find it, there we go, 6.67 times 10 to the minus, parentheses, minus 11, okay, times 5.94 times 10, times 10 to the 24, and that is divided by 6,384, well, yeah, okay, 6,384 kilometers, and then I'm just going to tack 3 zeros in the end to make it meters. So I'm not going to do the 10 to the whatever for that. And let's see what we get. And look, right there, 9.72. And this is going to be, so acceleration is going to equal, our acceleration here is going to equal 9.72. And so let's check our units here. This is going to be this thing here. So this is going to be, I'm going to just do units for this. This is Newton meters squared per kilogram squared. And mass of the Earth is going to be in kilograms. So and then we're going to have raise the Earth in meters squared. So what do we have here? We have cancel, 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 cancel. And it's newtons per kilogram. So, and that's actually kind of interesting. So I'm going to say newtons per kilogram. But what is a newton per kilogram? Well, a newton, you'll recall, is a kilogram meter per second square, right? So actually, the kilograms canceled. So really what this is 9.72 meters per second squared, which you'll notice is pretty close to G. And it probably would be exactly G if I don't know. Well, one of my numbers might be a little bit off. I mean, I might not be remembering this all quite as smoothly as I think I am. But you get the idea, though, that basically when we use this equation to calculate the acceleration of a small object near the surface of the Earth, we get little g. So I'll say approximately equal to little g. I got it wrong a little, but you know, the Earth is kind of what do they call it, like an oblate spheroid. It's slightly fatter on the sides and the top, and you know, different densities of crap at different places. Blah 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 blah. So anyway, that's my excuse for being wrong. So anyway. That's one little example of how to use universal gravitation, and we'll do a couple more coming up.